S. Chand presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Hello everyone. How are the ingredients in our common household disinfectants related or similar to those in wood preservatives and even in our photographic plates? Let's find out. I am Dr. Sujata Sengupta. Welcome to the S. Chand Academy. If you want to learn more about today's lesson, then please refer to the books by S. Chand Publishing, the link to which is provided in the drop box below. So let's begin our lesson today. So, what was the common ingredients that is common in all of these three disinfectants, wood preservatives, or even for developing photographic plates? Well, it's phenols. Phenols in the industry, they are found almost everywhere. They're used to make plastics, explosives like picric acid, and even drugs like aspirin. Our common household cleaners will contain phenols. Wood preservatives, they contain phenols which are known as cresols, and even the development of photographic plates will take place with the help of phenolic compounds. So in today's video, we are all going to learn about the chemistry of phenols. I hope you have been following our channel. If not, please do go back and refer to the videos on the chemistry of alcohols in this S. Chand Academy. That will help you to brush up as we quickly go over the chemistry of phenols. So let's get started. Alcohols, as you know, they were organic compounds which contained an hydroxyl group. They were one of the most common and versatile compounds which are found in nature, found in the industry, and even found around our house. Similarly, compounds which contain a hydroxyl group which is attached to a carbon, part of a benzene ring, they are known as phenols. So in general, phenols refers to a family of organic compounds which are characterized by a hydroxyl group bonded directly to the carbon of a benzene ring. Besides serving as the generic name to this class of compounds, phenol also refers to our simplest member, monohydroxybenzene, also known as benzenol or carbolic acid. In fact, phenol gets its name of carbolic acid because it originally was isolated from the acidic fractions of coal tar. Phenol itself, it is toxic, it is a neurotoxin. On our skin, it causes burns, and it is caustic in nature. Originally, phenol used to be used as an antiseptic. Nowadays, in a more dilute solution, it is found, for example, in commercial products like our mouthwash. It's also the key intermediate to many explosives like picric acid. Less toxic versions of phenols, for example, include butylated hydroxytoluene, which is commonly found as a common antioxidant in our various processed food products. Nomenclature. So how do we name our phenols? Because phenol structure also involves the basic aromatic ring, so all the rules pertaining to the nomenclature of aromatic compounds are also going to be followed when we name our phenols. The terms ortho, para, meta are also going to be used in this case. Certain phenols, they will have common names. So for example, our methyl phenols are commonly known as cresols, and our benzene diols have special names like catechol and resorcinol. Similar to alcohols, phenols, remember, they also contain the hydroxyl group, just that it is bonded to a benzene ring. So similar to the alcohols, our phenols are also going to be polar molecules. And so they also will show hydrogen bonding. So as a result of this hydrogen bonding, they will have higher melting and boiling points. And as a consequence of hydrogen bonding, they're also going to be soluble in water. In general, the phenols, they occur as liquids or white colored solids at room temperatures, and in general they tend to be toxic and caustic. Coming back to our simplest phenol, its physical properties. So it's a colorless crystalline solid. It tends to form a pinkish color if it is left exposed to the air, and it has a sort of characteristic smell with a melting point of 43 degrees. Now, although phenols are considered as simply being aromatic alcohols, but they do have certain properties which are quite distinct from that of the alcohols. Remember, alcohols were weakly acidic in nature. What does that mean? That means in the presence of a strong base, we are able to abstract the proton in the hydroxyl group to form our alkoxide ions. Now, phenols, they are stronger acids compared to alcohol, but not as acidic as carboxylic acids. What makes the phenols more acidic than the alcohols? Well, the phenoxide ion, which is produced when the base abstracts the proton from the hydroxyl group in phenol. These phenoxide ions, they show an unusual stability. They are resonance stabilized. So due to this resonance stabilization, the phenoxide ions are extremely stable and phenols will have a high acidity. The pKa of phenols tends to be around 10. Remember, our common alcohols would be around 16. Most phenols can be deprotonated when they're treated with sodium hydroxide. So let's see what happens. I have my base, this comes in and it abstracts my proton, and it results in the formation of my phenoxide ion. This phenoxide ion, if you notice, it will be stabilized through resonance. Finally, we get our final structure. So, due to this resonance stabilization, the phenoxide ions are more stable than that of our alkoxides. And therefore, the phenoxide ions can very simply be prepared by treating the phenols with an aqueous solution of sodium hydroxide. We don't need strong bases like the sodium or potassium metals. Now, if I had given you para-nitrophenol, do you think it would be more acidic or less acidic than my simple phenol? How will you find the answer? Simply draw the corresponding phenoxide ions, and I'm sure you will be able to say whether our para-nitrophenol is going to be more or less acidic than our common phenolic molecule. Now, coming to how are these phenol molecules prepared? Most of the phenols which are used today are prepared from benzene, either by the hydrolysis of chlorobenzene or from the oxidation of isopropyl benzene, also known as cumene. In the first step, which is known as the Dow's process, benzene is first converted to chlorobenzene by a nucleophilic substitution reaction, after which the chlorobenzene is treated with an aqueous solution of sodium hydroxide under high temperature and pressure conditions, and then it forms our phenol. But the more common method of preparing phenol is from the oxidation of isopropyl benzene, which itself is also made from benzene. Oxidation of isopropyl benzene, also known as cumene, first produces cumene hydroperoxide, which then undergoes an acid catalyzed rearrangement phenol. Now, this method may seem a little complicated to you. You might have preferred the Dow's process, but remember that in this oxidation of cumene, you are able to prepare two very important commercial products, both phenol and acetone. And that is why this is the preferred industrial method for the synthesis of phenols. So now let's take a quick break. But before the break, let me ask you a quick question. What type of reactions do you think phenol would typically undergo?
हाय, मैं हूं नेहा शर्मा और मैं आ रही हूं एस चांद अकेडमी में आपके फिजिकल केमिस्ट्री के डिफ़िकल्ट कंसेप्ट्स को इजी बनाने। सो प्लीज़ हमारे चैनल को सब्सक्राइब करिए ताकि आप अपनी सारी फिजिकल केमिस्ट्री की प्रॉब्लम्स को भूल जाएं और सबके सॉल्यूशंस आपको मिल जाएं।
Welcome back to the S. Chand Academy. Remember, before the break, I had asked you what type of reactions would you expect these phenols to undergo? And so, if you had said that they too would undergo electrophilic aromatic substitution reactions, which are typical of aromatic compounds, you are right. So, let's look at some of the reactions of these phenols. So, many of the important reactions of phenols, it is derived from the aromatic character. And so, similar to benzene, phenol will also undergo electrophilic substitution reactions. But in fact, electrophilic substitution on phenols is going to be much easier than benzene. Why? Yes, it is due to the presence of this hydroxyl group. Phenols are highly reactive towards electrophilic aromatic substitution because the hydroxyl group in phenol, it exhibits a strong activating effect on the benzene ring. It provides a ready source of electrons into the benzene ring. Not only are phenols activating, but they are also orthopara directors. So let's quickly take a look at this. So here I have my phenol molecule. So you can see that here through resonance, the electrons on the oxygen are going to be involved in conjugation with the benzene ring. Let's go ahead and draw all the possible resonating structures. Keep moving our electrons. All right, and so now you can see that it is at the ortho and the para positions which are activated towards electrophilic substitution. And so phenols, not only are they activating, but they are also going to be ortho-para directing groups. This activating nature of phenols is so strong that you can carry out the electrophilic substitution reactions without the presence of any catalyst, and at many times polysubstitution will take place. So let's look at a few examples. With dilute nitric acid, phenol undergoes nitration to give a mixture of the orthonitrophenol and the paranitrophenol. When we take our common nitrating mixture, then phenol undergoes a complete nitration to give the 2,4,6 trinitrophenol, which is commonly known as picric acid. The reaction of phenol with concentrated sulfuric acid is going to be thermodynamically controlled, and whether we get the ortho sulfonated product or the parasulfonated product will depend upon temperature. At lower temperature, our ortho product predominates, whereas at higher temperature, it is the para product which predominates. Phenols will react with halogens to yield either the mono, di or the tri-substituted products depending upon the reaction conditions. So for example, when phenol is treated with an aqueous bromine solution, then all the ortho and the para positions will get brominated, and we end up getting the 2,4,6 tribromophenol. However, if the same reaction is done under low temperatures using carbon disulfide as our solvent, then monobromination takes place. Other reactions which are typical to that of phenols will include the Hoben-Hosch reaction. Here, polyhydroxyphenols will undergo acylation in the presence of a nitrile, hydrochloric acid and over anhydrous zinc chloride. This particular Friedel-Crafts acylation with the nitriles is commonly known as the Hoben-Hosch reaction. Another common named reaction of the phenols is the Riemer-Tiemann reaction. Here what happens, the orthoformylation of phenols will take place and phenol is converted to salicylaldehyde. This reaction is also an example of an electrophilic aromatic substitution, but here our electrophile is our dichlorocarbene. The Kolbe's reaction is an example of the reaction of the phenoxide ion with carbon dioxide, and it produces a carboxylate. So for example, sodium phenoxide, when it reacts with carbon dioxide, it produces the sodium salt of salicylic acid. So finally, let's look at one typical reaction of the hydroxyl group in the case of phenol, and this is our Schotten-Baumann reaction for the preparation of the phenyl benzoates. These are common derivatives which is prepared by students in the undergraduate organic laboratory during qualitative organic analysis. Here what happens is that the phenol is treated with an acid chloride, usually an aromatic acid chloride, for example benzoyl chloride, in the presence of a base like sodium hydroxide, where it produces the crystalline phenyl benzoates which can be used to characterize a given phenol. So let's quickly look at this reaction. Here phenol is treated with freshly prepared sodium hydroxide, to which our benzoyl chloride is added, and we finally get the phenyl benzoate. How does the reaction happen? So I have phenol. When it is treated with sodium hydroxide, you have guessed it, it forms our sodium phenoxide. This phenoxide ion can now attack the electrophilic carbon present in benzoyl chloride. So let's do that. And what do we end up getting? So with the loss of the chloride anion, we end up getting our phenyl benzoate. It is important here that we maintain the alkalinity of this reaction with this freshly prepared sodium hydroxide solution. The completion of the reaction is usually characterized with the disappearance in the smell of benzoyl chloride. So with this, we have completed today's lesson. I hope you have understood the chemistry of phenols. We had looked over what are phenols, we had looked at how they are prepared, and we had looked at some of the chemistry of these phenolic compounds. I hope you enjoyed today's video. Don't forget to like, share and subscribe, and hit the bell button to stay tuned for further videos in the S. Chand Academy. Thank you.